So we can go to the next talk. Next talk is by Vishal Baibhav. So Vishal, could you please show your, Vishal, please unshare your screen so that
Yes, just a moment.
Vishal can go.
Not able to exit.
Just at the bottom, Vaishak. Stop sharing.
Yes, okay.
Yeah, we're done. Thanks. So Vishal, could you please share your screen?
Yes, can you okay, so the first question is, how do we form, let's say, a mass gap event, right? So of course, this is almost impossible, let's say, if we talk about, let's say, any event that is coming from field because of the pair instability or positional pair instability supernova. The other thing is, okay, so there were a few models which were, let's say, they were assuming, let's say, some funny convection, or let's say very, very small metallicities, and they were able to, let's say, somehow replicate large masses, right? But what those models they cannot do is they cannot get large spins. In fact, one of those assumption of those models was that you need almost a zero rotation to form a mass gap event. And like I said here, so in this case, this is the chi-effective chi-p plane, and this is the distribution of the second generation merger. And this is the black line is the posterior from 1905-21. And they agree to very, very good extent, I can say.
Sorry, Vishal, I think I didn't explain my question clearly. So what I meant is, I mean, I'm sure your model is fine. I'm asking about the waveform models used for the estimation of 1905-21, because I know for the fact that, you know, different waveform models give different results for the spin as well.
But okay, yes, definitely. So definitely that is the case. I do not remember which model. So these posterior samples, they correspond to which waveform model. But no matter what model we choose, okay, so for 1905-21, things were not as bad as, let's say, 1904-12, if I remember correctly, right? So even if, let's say, we were to choose a different model, this would not change any of our results.
Yeah, I'm not too sure that's right, because if you use I mean, it also depends on the priors you use, depends on the, I guess, if there's eccentricity or not, and a lot of other things. But yeah, I guess
okay,
yeah,
that's what you
but
mean.
I guess the chi-effective and chi-p would still be pretty uncertain.
Okay, I see. So yeah, we have absolutely no information about this eccentricity because, of course, there are not, at least at that time, there were not enough templates which have both precession and eccentricity, right? So
yeah, I still think there are not a lot of templates with both precession and eccentricity very well. But yeah, thank you. I think I got my answer.
Okay, so there is another question, but I will just ask my question quickly because it is related to what you people are discussing. So as far as I know, and means in LIGO templates, means they do not care much about the angle between the two spins, right? But you are having dynamically formed systems. There are so many 3-body and maybe even few 4-body interactions. So it is quite likely that two black hole spins will be directed in different directions. So are you planning to include that in your simulation?
Okay, so let me understand the question properly. So in this case, okay, so at least in this case, we are not concerned with, let's say, triples. So we are dealing with clusters. Of course, you can have, let's say, multiple binaries. They can interact with each other. They can form, let's say, something. They could form something, let's say, triple or triplet, right?
No.
But,
Sorry, I'm not thinking about triplet. But say if you have things in clusters, even if there is no direct mergers, but say your initial black hole was dynamically formed, then there was no reason that two spins will be aligned, right?
No, okay, so in clusters, yes, there is no reason the two spins are going to be aligned. And actually, you can see this from this distribution as well. So this is the chi-effective, and all the distribution I'm showing here, they are symmetric around chi-effective equal to 0, which means that you are as likely to get two spins which are pointing up, and it's the same probability as two spins pointing down.
No, but it can happen that one is pointing up, one pointing down, or there is say 30-degree angle between them. So that you
Okay,
have
so
got it.
this is already included here. So this, okay, so the distribution I'm showing here,
Mhm.
it is kind of marginalized over different
Spin
spin
angle.
Yes.
So this is spin angle with respect to orbital angular momentum or spin.
Yes.
But I'm trying to understand the spin between two angle between two spins, not.
The yes, that is also something that we marginalize over as well. So
Okay.
yes, exactly.
Okay, that's good. So because that I find always very interesting. Okay, thank you. So Kaustubh, please go ahead with your question.
Yeah, I have a very short question. So looking at these plots for the 1G plus 2G and 2G plus 2G, I see a sub cutoff at 0.7. And I expect that it is coming because of the heuristic average of chi-p that you're using.
Yes,
And,
exactly. So
and I have also find that the chi-effective terminus close to 0.7, right? But I'm not really understanding why there is this bend like structures that you are seeing out here, both in the banana shape that you see in 1G plus 2G as well as 2G plus 2G.
okay, so yes, exactly. So in this case, I am only talking about, like you said, the heuristic chi-p that LIGO uses. But okay, so and this is what I'm only showing, at least in this talk. But if you go to the paper mentioned here, we deal with both the, let's say, the generalized or the asymptotic chi-p as well. And in that case, like you said, so the heuristic chi-p, they kind of have this unnatural kind of maximization, right? And this is why you see this cutoff at least 0.7. So yes, exactly, I agree with you. Does it answer a question though?
Yeah, but I was wondering why this bend like structures that you see at the lower chi-p values. That's the thing that is
so what do you mean bend like structure?
like if you look into 1G plus 2G, you see a horseshoe like shape, right?
Yes.
So what determines the lower limit of that horseshoe?
Oh, I see. Okay. So in this case, so for example, let's say we are assuming that the black hole is the first generation black hole. It has very small spins, right? So this kind of makes sense because you have both black holes, which are, okay, so you have, so for example, okay, so let's say, look at this. So which means that the chi-p is almost 0, right? Which means that there is no in-plane component. So if you were to calculate chi effective, it should go like chi1 plus q, chi2 over 1 plus q, right? So if the mass ratio is 0, it should go like 0.7 by 2 and 0.35. This is what we are getting here. That answers the question, right? Okay. So basically what you get is kind of an ellipse with, so this is an ellipse, honestly.
So maybe, yeah, maybe technical details you can discuss offline.
Okay.
Sorry, because we are getting late.
Yeah, I understand.
Yeah. Okay, so let us thank Vishal again for this interesting talk. So now our